Is this working? Oh, okay, I think we're working. Cool. This is gonna be the first, or the zeroth episode, the zeroth video in a series that I'm trying out, where we will be solving some problems on LeetCode. So I'm, just to give an intro, I'm Billy. I'm an engineering manager at a startup in Silicon Valley, and I conduct a lot of coding interviews for candidates, and I've done a lot of coding questions myself, so I thought it would be useful to do a series on solving some problems live. So I'll be essentially just going through a bunch of LeetCode problems and talking through solutions and kind of how I go about solving them, and then we'll go through just the live practice of solving some problems. All right. Since this is the very first time I'm going to be trying this, we'll start off with just two-sum. I opened a fresh LeetCode account, so there's nothing that's solved here. So we will give this a try. Hopefully this is all visible to everyone. Cool, so I guess I'll just go through the problem. So given an array of integer nums and an integer target, return indices of two numbers that add up to, return indices of the two numbers such that they add up to the target. You may assume that each input would be exactly one solution, and you may not use the same element twice. And you can return the answers in any order. Typical two-sum problem here. All right, so we have some examples here. Nums, you got your clear sorted nums. Target is 9. You find that there's exactly one solution, and it's those two. Here we have, unsorted input 3, 2, 4. You find two numbers that add to 6, and so that's 2 and 4. Here you have 3 and 3. So then you find two numbers that add to 6. So that's 0 index and the first index. So the way I typically approach these problems is starting off with a naive solution. Right. So how do we find two numbers that in an array that add up to a target number? Well, the naive solution, let me write this down here. So we have the naive solution, which is to something like an n-squared solution, where you go through each element in the list. So you for each element, and then for second element in the list, second candidate element, if sum of 1 plus 2, e1 plus e2 equals target, then we return. So something like this is pretty clearly n squared, in the case of these problems, there's usually some constraints here that tend to indicate what the time complexity of the solution is. And so here you can see that the length of the numbers goes up to 10 to the 5. And then you have obviously the constraints on the actual numbers themselves. So usually 10 to the 5 is your big N, right? And you want to find solutions where the time complexity of your biggest N is somewhat reasonable. The definition of somewhat reasonable here is usually about a couple million operations. That's kind of what I've dealt with in the past here. And so, if we're looking at an n-squared solution for this problem with max input 10 to the 5, then that means that you have a 10 to the 10 runtime, right? 10 to the 5 squared is 10 to the 10. And if your runtime is 10 to the 10, 10 to the 10 is, what is that, like 1 trillion? Right, that's 10 zeros. It's like 10 trillion. Or is that right? So 6 zeros is a million. Another 6 zeros is a billion. Oh, so it's 10 billion. 10 billion is pretty big. So we're probably not going to be able to solve this question with a linear solution. We're probably not going to be able to solve this question with a n-squared solution. But we can give that a try just for fun, just to code up what's going on. So yeah, and one thing we can actually do here is optimize this solution a little bit more. All right, this background music is actually making it hard for me to talk. Here, let me pause this for a sec as I explain something. All right, so this is very naive, where we're kind of like looking at each element in the list and then blindly looking at the second element in the list, like another element in the list, and we just care if they're not the same element. But that would involve us kind of like looking at the same element more than once, or like the same kind of combination more than once. Right? So imagine like we start at 2, and then we as our first element, and then we look at all the other candidates, and assume that like we don't find it with the 2, and then so we move on to the 7 as our first element. If we do a naive n-squared approach, then we actually start looking at the input from the 2 again, and then go forward. But we already looked at 2, 7, and that didn't work. So we actually from 7 only have to look at numbers that occur after 7. So if you do a solution like that, then what you're doing is something like for first candidate element, we look at for second candidate element occurring after first candidate, then you do the same thing here. So this is actually, seems like not a huge optimization, but it's actually pretty big. So what this does is actually it changes our runtime. So runtime becomes, so you have n on the first pass, right? You have like the first element and then checking every other element. So it's like n minus 1. But then the second pass is you're starting at the second element and checking the rest of the list. So it's not actually something like n minus 1 plus n minus 2 plus n minus 3 plus, and then once you're looking at like the later elements in the list, you know, you're only looking at like a small number of elements after that. So this actually ends up going to plus 2 plus 1 in the end. And then the sum of this is actually, so this is just the sum of arithmetic sequence. And so this becomes, you know, the first plus the last over 2 times the number of numbers. So that's like n over 2 times n minus 1, which is actually n squared over 2. So this is actually 2 times faster than our previous naive solution, which can be significant if you're kind of on the cusp of, you know, meeting the performance requirements for these problems. So we're just going to do the smarter n-squared solution as a demo first off. So what we want to do is look at our inputs. So we want to go for first in range length of list, length of nums, for second in range first plus 1 length of nums. Oh, let me actually start the timer as well, since we want to kind of time how long these take, just for my own interest as well. Let's see, make sure my stream is all right. Cool. Alrighty. Okay, so am I like dropped? Oh no, I'm going. Okay, cool. Yo, Vincent, hello. I'm just solving some coding problems as a test thing of streaming. Thanks for showing up. Right, so what are we doing here? So we're comparing these numbers now. So if nums at first plus nums at second is target, then we're done. So we want to return this list of first, second. Cool. Now we can run code here. Ganbate, thank you. Cool. All right, we passed the test input. Let's try the other test input. 3, 2, 4, and 6 should pass. I'm pretty confident in our code. Let's try 3 and 3. Oh, I got rate limited because I'm not a pro in LeetCode. Nice, that passed. Let's try something like 2, 2, 3, 3, which should return the last two. Cool. We're going to submit because why not? I doubt this is going to succeed without a timeout, but we'll see. Cool. Right, so we got time limit exceeded as expected. There's just a lot of kind of pain in here. So what we want to do now is optimize this. So how do we optimize this? So from here, normally I would just consider, so we're at n squared right now. How do we get faster than n squared? So faster than n squared. That looks like either like n log n log n, constant, right? So those are options. If we're lazy, then we can do a n log n solution here. So the kind of typical thing that people know about these two-sum problems is that, well, I guess there's the common solution here of solving this problem in n time, where so when you have an array of numbers that sum to a target number, if you just look at a single candidate, right? If you're looking at what one of the numbers is, then you take that number and subtract it from the target, and then that's the new target number you have to find as a single number. So what you can do is, with some memory, you can go through the list, and then for each number in the list, you subtract it from the target number, and then that indicates to you that there is that you would need to find a number of that value. So let me just do an example here with this 9. So if your target is 9, you go through the list. You start at 2, you subtract it from 9, and you say, okay, if I pick 2, I would need to find a 7. So you store that 7 in a hash table. And then you come to the 7 now, and then you say, is 7 in the hash table? If it is, of numbers I need. If it is, then I'm done. If it's not in the hash table, imagine this is like a 1 or something, then you subtract 7 from 9, and then you say, okay, I need to find a 2 in the hash table. You put a 2 in the hash table of numbers you need to find. And then you do that with all the elements of the list, and then you run through all the elements of the list again to double check and see if any of these elements were previously found and stored in the hash table. So that's the 2-pass ON solution with ON memory. It's kind of a typical pattern you see here in this problem. If you wanted an n log n solution here, what you could do is sort this list and then kind of do like a 2-pointer solution from the front and back, and kind of look for two numbers that sum up to the target number. And then if your current sum is too big, then you decrease the index from the right, and then if your sum is now too small, then you want a bigger number, so you increase the index from the left. So that is the solution for the n log n, but we're just going to do the n solution with the hash table. All right. This is actually pretty difficult to explain these problems without, well, in this case it's hard because I already know the solution for 2-sum because it's very common. and I've seen it before. Maybe it'll work better once I kind of pick a random problem, which is the original plan. This is kind of just warm up, getting used to this environment again. All right, so let me clear this out for the first solution. So we're gonna do the end solution where we store things in a hash table. The tricky thing here as well is that because you could have two elements or more than one element that is the same, and you need to return the indices, then the difficulty becomes, if you kind of apply the solution to this this input, right? You say starting at 3, I need to find another 3, so I put a 3 in the hash map. If I get to this 3, I potentially, I need to like know about the first 3, and then need to know that it's not the same as my current 3. And so what you actually need to put in the hash map is like the indices of these numbers, and then when you do the lookup, you just make sure you grab a number. So if I do like the first pass in here, I would store for the key of 3, there's a 3 with index 0, and then for this number, I would store in the hash table for the key of 3. There's also 3 with index 1. In this case, actually, I would probably be able to solve the problem because I look up in the hash table, there's a 3 of index 0, and then I would return. I actually think that should be fine as well, because if there's two numbers of the same value, then you're bound to find 2 of them, and you won't have collisions if you go through the list in one pass. Right, so like here I actually don't care about, I can always answer this in one pass if it's like n/2, n/2, and my target is n, because the first n/2 I'll dump it into the hash table, and then the second n/2 I can check the hash table already, and I would have seen that the previous n/2 is in the hash table, and so I can just return. Okay, so then I don't think you need to store the indices. I think you just need to store the values. Well, actually, you do need to store the indices because you have to actually return the indices in this case. You can probably just overwrite the indices. Yeah, I'm fine with that. Yeah, since there should only be exactly one solution. So we're going to do something lazy where we are looking for something like key is like new target to index dict. Here we go. So this is just going to be an int to int dict hash table, int to int hash table, and then we're going to do this in 2 passes. So for iron range nums, value equals nums at I, new target equals target minus value. So then if new target is not in your list here, then we just add it. Yeah, that's fine. At new target equals is I, else. This is like pretty poor coding. I would probably clean this up a little bit if I were doing this again. So if new target is in the thing in the dict here, then we're done. So then we can just return. Do you have to return these in order? You can return the answer in any order. Nice. So we're going to return I, and then like a index here, new target, index like new target, and then I. And then we do the second pass of for iron range nums. Yeah, pretty much doing the same thing here. Returning. Cool. This should be successful. Okay, this was not successful. How's my output thing here? All right, let's debug this. This looks right. Val is nums at I. New target minus is target minus val. So this should be like 4, right? Because our target isn't changing. 4. If 4 is in there, 4 is not in there, you put in 4, 0. Otherwise, you return index of 4 and the current value, current index. You come through here. So this should have gone through and found the 3. The 3 would be inserted into the all right, we're just gonna print things. I'm too lazy to figure this out right now. Huh? Oh, whoops! I'm putting in val. If val is not in there, wait, no. This should be new target, right? No, there should be val. Whoops. That's what I want to do. So if the value is not there, then we stick the value in there. And then we should check if value is in there. Yeah, let's solve this problem right here. So if val is, actually, no, let's do this. So we actually want this. Okay. So if the new target, oops, deleted this new target line here. I'll need to print. So we first try to see if the new target already exists in the list. If it's in there, then we're done, right? We can return this thing. Otherwise, we are doing our normal stuff. So now, if val is not in the array, then we put val in there. And that's about it. And then we go in again. This should, I suspect this will work. Cool, that looks right. Let's do the other ones. Cool, that looks right. Something like this should also return O2, that looks right. 3, 2, 4, and 6. Cool. And then 3, 3, and 6. All right, cool. Let's submit our ON solution. Yes, we did it. Cool. All right. That was a problem. We solved one problem. How long did that take? That took us 15 minutes. Wow. Well, we also just went slowly and talked through things. All right. Let's pick a random problem and go. We'll see how this goes. Okay. Bitwise OR of subarrays. This sounds annoying. All right. So let's do this problem. So we have an array A of non-negative integers. For every contiguous subarray, we take the bitwise OR of all the elements in B, the subarray, containing a result. Okay, right. AI blah 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 blah. Return the number of possible results. Results that occur more than once are only counted once in the final answer. Huh? Oh, like the different the different bitwise OR answers of all subarrays. This is kind of annoying. So here we also have, so this is contiguous subarrays. What is the naive solution? So you just find all contiguous subarrays, take the bitwise OR, and then output the answer. That's pretty annoying because taking the bitwise OR, if you're doing it like in a naive way, is already n on, and then you need to find all of the subarrays, which is real annoying. What is that? That's like, man, I'm pretty rusty here. What is the number of subarrays here? So if I take the first one, I have n subarrays, right? I have just the first one, the first and the second one, 1, 2, 3, all the way to 1 to n. If I take the second one, I go to blah, blah, blah. So then, okay, so the number of subarrays, let's do the math here. Number of subarrays, you have like, again, n plus n minus 1 plus, blah, 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 plus 1. So you have, what is this, like roughly n squared over 2 subarrays. And then it takes n to calculate the bitwise OR if you're doing it naively. So that's n cubed, an n cubed solution. And we have an array length of 50,000. 50,000 cubed is gigantic. Okay, that's like 10 to the 5 cubed. 5 cubed times 10 to the 5 cubed, which is huge. Meaning we need some smarter way to find the bitwise OR of the subarrays. So what I can immediately think of is, if you had a subarray, let's see where this goes. So if you had a subarray of like AI dot 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 AJ as your subarray, then you know that the bitwise OR of this is equal to the bitwise OR of AI, or the bitwise OR of AI plus 1 to AJ. Or alternatively, let's do it in the other direction, because I feel like that's probably easier. Something like this, right? Of J minus 1 or AJ, right? So you actually, does that help you at all? Right, so then it turns your bitwise OR operation into O1, because now you just have to store the previous solutions, right? So if you always know the previous solution, then you're only doing one bitwise OR. So now we're at n squared, which I think is acceptable here. 10,000 squared, 10 to the 5, no, 10 to the 4 squared is about 10 to the 8. That is like 10 billion. This is like 250 billion. That's a lot still. We'll see if that's acceptable. Yeah, this is the primary idea. So we're going to memorize and store the solutions of this past solution, and then yeah, do a bitwise OR in such a way. Yeah, I think that might work. Cool. So previous ORs is a 2D array. Something like 0. How do I want to do this? I was thinking of doing a 2D array of like start and end. So array at start, at end, index, and then that value of that index is the bitwise OR of that contiguous subsequence. I think that's fine. All right, so this is 0 for I in range length of A, for I in range length of A. Does this even work? Yeah, this should work. Print length of previous ORs. Print length of previous ORs at 0. Pretty sure this should work. Cool. All right, let's do this. Okay, so what we want to do here is also store the different possible answers, which is a bit annoying to store, but that's fine. So we have possible answers as a set, and then we just go through, right? So we fill in, so let's fill in subarrays 1, length 1. So for I in range length of A. Previous ORs at I equals A at I. Now do the memoization, do the algorithm. So what we want here is so starting at 0, you want to do a for loop. Yep. So for start in range A, for end in range start plus 1, length of A. So then you want to do previous ORs at start at end equals previous ORs at start at end minus 1 or A at end. That will populate the list. Or values. Or value is this. Or value possible and dot add or value. Let me also do possible and dot add and I want to print length of possible ands. Who? Oh, we want to return. Whoops. Nice. We did it, boys. Nice. We got him, boys. Nice. Submit. I don't think this is going to work. I think this is going to time out, but we'll see what happens. Oh, yep, we timed out. Oh, this test case is big. Can we copy this test case? Will this time out if we run it locally, is the question. So this solution is O n squared over 2. Pretty rough, if you ask me. It looks like we might need some sort of n log n here. I don't know how you would do that. Or if you could maybe do the ORs differently? I am curious. So I do think, what are the subarrays I'm looking at right now? Right, so I look at subarrays of length 0. And then for subarrays of length 2, I'm always looking at I, or taking like I plus 1, ORing I. And for subarrays of length 3, I'm always taking I plus 2 and ORing that with the previous value. Can I do less ORs is the question. I don't think so. Well, I mean, I'm sure we can. What do we want to do here? So I was thinking something along the lines of maybe storing more subarray values and then only using subarray values that you don't know. So, right. So what I mean by that is right now we're looking at something like A at 0, then A at 0 to 1, then A at 0 to 2, ... right? But for A at 0 to 2, we actually, if we know A at 1 to 2, so A at 0 to 2, the OR of A at 0 to 2, right, I'm just going to not notate that, is equal to like A of 0 or A of 1 to 2. But that operation is equivalent to doing the OR the other way. So I don't think that matters, actually. And yeah, that doesn't help us here. Is there a way to reduce the number of subarrays? No, because you need to look at all subarrays, I believe. Yeah, I'm pretty sure you need to look at all subarrays. Let's table that as well. So this thing cannot be necessarily reduced. Can we speed this up? Probably not. Adding to a set, I'm sure under the hood they are not adding to the set if it already exists in the set. But we can add that check. This took 3,000 milliseconds. I really don't think this will be faster, but it's worth a try. Oops. That was wrong. Ooh, that took longer because we did the extraneous check. See, I thought so. Just run this to make sure it is actually 100 milliseconds faster. That's roughly. Is there something we know with Bitwise OR? If this is like a bit trick, I'm going to be annoyed. I don't think these necessarily have a lot of value unless you're working with bits all day directly, which I don't think most engineers are. Okay. Oh, I forgot to start a timer. Dang it. Oops. Well, this is untimed. It will be timed on stream on the pod. All right, so we need to make this faster. Do we need to look at all subarrays? I feel like we do. Right, even if you have yeah, is there a way you can know beforehand? If your subarray is no, I don't think so. Yeah, I don't know. I don't know what you do here. Fill in the subarrays. Yeah, because this is equivalent. All right, let me write some stuff down. This is equivalent to A at 0 to 1 or A at 2, right? It's the same op. So you're telling me we need to do it faster than n squared over 2? We need to do faster than n squared over 2? Bruh. How are we going to do that, bro? I mean, the bitwise OR... Is there like a faster way to do bitwise OR? I don't think so. Nor can you really tell beforehand what the result of the bitwise OR is going to be without doing it. Dang, we're stuck. We're stuck here. Alright. Take a breather. Check my phone. Drink some wine. Is drinking wine allowed on stream? Alright, too late. It's juice. It's juice. Just some grape juice. What do we want to do here? This is difficult. Alright, the number of subarrays I don't think you can reduce, right? Because you need to know... Okay, let me reread the problem. We have A non-negative integers for every contiguous subarray. Take the bitwise OR of all elements in B, obtain the results. Return the number of possible results that occur more than once are only counted once in the final answer. Does that really speed anything up? Whoa! Whoa! There's no way that's 500 milliseconds slower. If I set a list versus adding each element into the list into a set, okay, it's just variable runtime. That's still both those runs were slower than when I added it individually. What? What is happening? Why is this taking 4 seconds? Okay, it's just variable slowness. Okay, that's fine. Okay, yeah, we need to make this run in like 2 seconds. I think that's about enough time. Alright, I believe that this is preferable here. Okay, so we fill in the subarray. Previous ORs or the next value. Put the next value into the list. And add that to our list of possible answers. What does time limit exceeded mean? Oh, time limit exceeded is that they run n test cases. Interesting. And you didn't run through enough of them. Yeah, I really don't know how you do this more quickly when each of these operations seems pretty quick to me. Alright, I don't think there's value in me just like struggling here with no leads. And we'll go to the discuss. Oh no! Oh, what? Java can just brute force it? C++ O(n) log n is time limit exceeded? What? Dang. Do we want to check the solution, guys? I don't want to. The inside of me doesn't want to do that. But I feel like we're not getting anywhere with this. Is there a way to do it in one pass? Or just many single passes? How would you do that? Because aren't there n squared subarrays? I don't understand. Maybe this assumption is wrong then. Alright, how many subarrays are there? If you go from 0, you have 0, 0, 1, 0, 2, all the way to 0n. Those are all distinct subarrays that have distinct values when you bitwise OR them, potentially. It is possible. The only possible thing I can think of is removing dupes. But then removing dupes, you can't remove them outright because you could have subarrays that include both dupes, one dupe or no dupes. Or, yeah. Yeah, I still feel like you need n squared subarrays. So you have n subarrays. Right, and then you have 1, 1, 1, 2. But maybe you already knew 1, 2 from doing 0, 2. That's not true though. You wouldn't have known. And even if you knew, you would have to do an operation to find it. So you have 1, 1, 2, 1 to 3, all the way to 1 to n. Maybe we must start from backwards. I don't think that's any better, but yeah, it really is just n squared over 2 still. I don't think there's any... Wait a sec. Okay. If you solve for n, if you have the subarray n, you know the bitwise OR. And then if you don't take the n, then you just move on to the next one. If you do take the n, then you have n minus 1 to n, which only needs to do once. No, that doesn't make any sense. Because then if you don't take the n, then you have n minus 1. But then you need like n minus 1, n minus 2. Which you don't know unless you do that operation. And you don't know it from the previous set of things you calculated because those were ending at n and not n minus 1. Yeah, I don't see how you can do less than n squared over 2 subarrays. All right, time to look at the discussion here. Getting TLE, how to optimize. Yeah, he's doing what I'm doing. Bruh. What is this trick about the OR operation? What the heck, 30n? What the fudge? The reason is that B01 is greater than B1I is greater than BII. B0 of 1 covers all the bits of B1 of 1. That's true. That is true. There are mostly 30 bits for a positive number. That is true. There are at most 30 different values of those. All right. Let me absorb what he just said into my brain. So your value of what did he just say? What did he say? B0 at I covers all the bits of B1 of I. Oh wait, what is he doing? Hash set cur store all. What the heck? All bitwise. Bij. Oh, it's from 0 to I. 0 to I is greater than or equal to 1 at I. Right. That's true. Oh, that's so friggin' bits, man. So annoying. Okay, so that means you're just storing the bits, the 30 bits, right? And then And then for each number, you look at all 30 bits and you see which ones are turned on or not. Right. And then based on the number of bits that are on in each position, then you know what's possible. Is that true? Say you have 30 bits, right? And like the first number takes up some number of those bits. The second number takes up a different number of those bits. You know that if you took them individually, they have no overlap. And if you took them together, they would have overlap. So they create a new value. What? How is this still 30n? Is there a way to do this? So let's use like a small example here. Let's write this down. So we have like 3 possible bits, right? Like this. If we have like 1 0 0 and 0 1 0, 0 0 1, right? And then 1 0 1. How many different bit values are there in these subarrays, right? So if you took each of the unique ones and there's no overlaps, then you're done. So this is 4, right? And then you look at the bitwise ORs. There's like the greater than or equal to thing is important here. I'm still not wrapping my head around what is it doing here. Duck, use hash set. Heck, subarray bitwise OR, use 2 sets. For I and A, current equals the set of I or J for J and current. Or I, and then result or equals current. What the heck? What is happening here? I don't understand. Result is empty though. Oh, but it's not empty. Wait, this doesn't make any sense to me. I don't understand the magic going on here. All right, let me look at this Java solution, or C++ solution. Observing that a.length is less than or equal to 550,000. I assume that O and score time complexity won't be accepted. Size of cur will be less than 32. All right, let me just read the solution. Elements between res left and res right are the same as cur in solution 1. I don't know what is happening, man. Cur is less than 30. All right, let me try to understand what the solution is doing. Cur equals I or j for j in current. Or I. So this is empty at first because cur doesn't have anything in it. So this is just I. Alright, so then you have the second value, j. Or second value, and then you say the second value is ORing everything in the first one. So then it's the second value or the first value? Oh, but it's bitwise OR, so there's a positioning doesn't matter. Okay, so then you have wait, what? That doesn't make any sense to me. Oh, you're ORing the sets, right? The sets. So you're saying, okay, you're adding that value. Right, so that you're ORing. So this is just getting the subarrays of 2, containing element ending with element I. And then this is where the magic, I guess, happens here. So the results, you're ORing with the current. So you're telling me that because cur Isn't this operation, why does this look like it's, okay, I don't understand what's going on. Cur.size is less than or equal to 30. How is this less than or equal to 30? Isn't this the set of values that are equal to n? Beta I and j are all different. And res.size is 30n. Oh, but these are all different, but there's only 30 bits. What? Wait, how are there at most only 30 different values for this? Isn't it 30? But can't each bit be on and off? Dude, I don't know what's happening here. Oh, okay. This is for all the subarrays ending in I. There's only at most 30 values. That is correct. Wait, no, that's not correct. What the heck? Hey, isn't this easily disprovable? Oh, it's not easily disprovable. It's in fact provable. Because if you tried to have values that were unique, right, you can only fill up each of the 30 bits. And then once you fill up each of the 30 bits, anything you OR with that fills it up. Damn. Is that true? Yeah, that's true. Damn. What the heck? This is the key. Okay. I understand the solution now. So we need to get all of the subarrays ending in I and then OR those. Okay. So let's wipe out the solution here. Get all subarrays ending in I. So yeah, so let's do ending in like n value, right? Wait, but isn't the construction of... Oh, it's the construction of this thing takes n time. And then this thing will be 30. And so adding it to a list is only 30. That's what it means. Okay. So, so my subarrays subORs equals set. Right. Actually, we can just do it constructively. This is like too confusing. Start +1, length better. If we do it constructively, then it's a little easier to read. So we want to do, so subors dot add a at start. And then we want to do here, previous OR equals a at start. And then we want to do so previous OR equals a at end. Subors not add previous OR. So this is all the subarrays starting with A, and then we need possible ands. Here we go. Ands ORs equals subors. Return length of possible ands. I think we did it. Oh, we lost the giant ass test case. Oh, we can get it. We can get it. We got it. We got it back. If this is not faster, I'm going to be very confused. Oh, it would run in half the time. Hopefully this doesn't time out. Oh, we TLE'd again. We got scammed. We got scammed. How did we TLE again? What, we only made it through one more test case than the previous one? Oh, does that mean we TLE'd on this new test case? What? We ran this new test case in 2 seconds. All right. I guess we gotta do this faster now. Maybe this is slow. This is N though. We got faster. But we still failed. Oh, we don't need previous ORs anymore, actually. Maybe, don't tell me that is slowing us down, okay. Oh, that was half a second. All right, we'll submit again. We'll see. We'll see if this passes. If this passes, I'm gonna lose it. Acceptable. Acceptable that it didn't pass. Oh, it passed more test cases, though. So that, I mean, that is like an n-squared operation to build an array, right? So I build the 2D array. Oh, this took 8.3 seconds? What? How long is this thing? What the heck? This is like 10,000. What? Isn't the input up to 50,000? Fudge. I suspect something weird is going on here. Don't tell me that set or equals is faster. I will lose it if this is faster than add. Yeah, it's not faster at all. What? I don't understand. Prove to ourselves that this is correct. I strongly believe that this is correct. We just need to prove it to ourselves. I mean, if the Python cannot pass, then we are just in trouble here. That's annoying. There's got to be some way to check, right? Like, this can't be it, right? Oops. Oops. What? No way. What? Hold on. So a equals not equals is faster than a set add? Is a set add is doing a lookup in your lookup table. That lookup, I guess it has to like hash the value and then do an array lookup. Isn't array lookup? I guess array lookup is slower because you're looking in what? I'm confused. I'm confused. Let's see what we got. Oh, we TLE'd again. What? I just passed in one additional case? Are you kidding me? What? How am I just like getting destroyed on all these cases, man? And this trick didn't work? This trick didn't work? What? This took 2.7. Is there like a way to do like a bitwise? All right, we're looking at the solution again. How come this thing is faster? I mean, he's literally doing what I'm doing. Unordered set is very slow when the size is big. What? This thing's not big though. Oh, it is pretty big. Fudge. So it might be this then. Maybe we're just getting Pythoned here. Okay, we don't need that. What the heck? Oh, that's actually better. Because this operation is n. So this should actually be faster. Oh, not really faster. Oh, because you still have to do a set add for each n. Right. Right. Because the fast part is this, which apparently is not that fast when n is big. So what we could do is split this into two. That seems so bad though. Like, do we really need to do that? Oh, fudge. All right, let's test out a theory here. If start mod 2 equals 0, possible ands 1, possible and 0, or equals suborders, else possible ands 1 or equals suborders, and then don't really, am I really doing this? Fudge. Possible and 0 or possible ands 1. Are you kidding me right now? Are you kidding me right now? Oh my gosh. Are you kidding me right now? Don't tell me this improves the speed. Otherwise, I will cry. Okay, that just made it worse. Which makes sense. That's about the same. I don't think we're gonna get any better than this. I still can't believe this is an optimization. Can't believe it. So what? Should you just check if A... Is that an optimization? That's only doing it n times though. I don't think that's an optimization. That can't be an optimization. That can't be an optimization. That can't be an optimization, dude. Yeah, it's not an optimization. All right, we'll just submit for fun. I really don't know how to optimize this though. All right, let's go line by line. And we don't need these sets. I mean, I don't think this length is really doing anything for us here. Did we also fail at the same 76? 76? Okay, we're making progress. But we also can't beat 50K right now. Is it better? No, it's not better. To add, I was gonna say, like, is it better to add to a list and then dedupe it at the end? But I don't think it's better. Okay, so we go through the start. We make a list of answers. List of unique answers. But I feel like you would have to know if you've seen it in a previous one before based on yeah, it's not good. It's not good. Okay. Previous OR. Get the new OR value. If it's not the same, then you add it. If it is the same, you just ignore. Okay. This is annoying. Dude, we're so close. All right, we're going back in the forums. This man's Python. Am I creating a new set here? No, I'm not creating a new set either. What? Dude, I don't understand this at all. What the heck? Also, why is this needed? Because doesn't this go through everything in the queue already? Why do you have to add A again? Because isn't A or A the same as A? Oh, because queue's empty at first. This doesn't make sense to me though. How is this faster? Is it because I'm making a new set every time? No, I don't think this is it though. I don't think this is the reason. What? This doesn't make any sense. Is set creation really that much? So that means if I move this outside of the loop, we're done. Don't tell me that this is the answer. What? That took 8,000 milliseconds. All right, we're saving that and we're taking this guy's solution. I don't understand how this solution is faster though. What? How did this take 52 milliseconds? What the heck? All right. Let's study this solution that's going on right here. Okay. So for A and Q, for A and A, right? So we take the first element. We do nothing. We add A to the Q. Add A into the thing. Second element. So we have A in the queue, second element. Oh, we already added A to the queue, so we're fine. So now we just look at A or B and B. Oh, this looks at much less elements, I see. A or B and B. And then checks them in the queue. The third one looks at C, CB, or like B or C, and then the previous guy or C. How does that differ from this one? This one I'm looking at A. All the way to the end. Yeah, I think I need to like draw this out visually. Oh, no, I'm doing this wrong. No. Wait, am I doing this wrong? Hold on. So we have A. Oh, no, that should be fine then. Yeah, so you are looking at n squared over 2 here. Aren't you looking at n squared over 2 there, though? Is it range? Is that why? Is range slow because it's creating a new thing every time? Don't tell me the answer is because range is slow. Okay. Don't tell me it's because range is slow, okay? Oop. Oh yeah, I think it's because I'm getting rid of the old list. Wait, I don't understand what is happening here. So I'm adding A to the list. I'm also adding AB to the list. Oh, but this thing is saying like also add B to the list. What? But how does that make things faster? Also, this is no longer contiguous, right? Oh, it is contiguous. It is contiguous. Oh, okay. So it's like for each new element you need, because you don't have to track all the contiguous arrays, you just have to track the contiguous arrays so far. Right, because any subarray would have already been countered. I see. Okay. Let me try to code this up then on my own. All right, so you want to get so you want to something like in the first iteration A, then A or B and B, and then you want A, B, C, B or C, and C, dot dot dot. Right, so all right, because your other guy will track things. I guess it's just like weird operationally. What was I doing before? I was doing like A or B, A, B, C. What? How's this different though? Versus tracking something like A or B or C, dot dot dot, A to N, and then you have B or C, dot dot dot, B to N, C. Well, I don't understand how these are different. So here you're throwing n things which you likely have less than n of, right? This is 30 things into the list. What? I just don't understand how the previous solution, this solution, is so fast. So I guess it's like not doing any loops. It is not creating any new numbers to iterate over. It is not creating new sets. Wait, that just doesn't make sense to me. maybe it is a code thing, like a underground, like a secret code performance thing. All right, we'll do it the other way. Oops. All right, we'll do it this way. All right, so something like for A and A, we want to do partial I mean, I'm just like, the solution was so short, I'm basically copying it. But it just blows my mind that this thing runs in 52 milliseconds. That's insane. All right, well, we spent a ton of time on that problem, but we solved it. We understand why it works. Well, we actually don't understand why that solution that provided is so much faster, but we'll think about it. You can also think about it. All right, that will be it for me. It is 11. I am pretty tired. Yeah. If you watch this, let me know if you liked it. I might do more of these. I might not. I think it's difficult to explain in this medium, to explain a problem. Or maybe I'm just rusty at explaining problems myself. But yeah, we'll see what happens. Yeah, that'll be it for me. All right. See you, folks.